We are picking up where we left off yesterday in stats with more sampling distribution, parameters, statistic definitions. Um, on, a, on the PDF that I attached to Classroom, this one was typed funny, so I've edited it. And it looks a tiny bit different at the very end, right here. I think it says something like of all adult females or something like that. And it's workable. It's worth talking about because the sample's not being taken from the group that's typed. But I still felt like it was weird, so I changed it. Maybe hit pause and try and fill in these blanks here, but I'm going to do it right now. So the population, because we took a sample of female college students, the population is all female college students. We don't have a sample size, so I'm just going to say a random sample of female, sounds kind of redundant, college students. Our parameter, you got to skim through it and look at what we're talking about. We're not talking about proportions this time, we're talking about means. So the parameters in regards to the population, which looks like it's this 63-inch height. So mu, the true mean height of all female college students is 63 inches. And then the statistic, naturally, will be the other number. That one I'm not too picky about using words. I just use symbols. So that's X bar, and it's 64.5 inches. All right. I hope that made sense. Please practice these. There's a couple more of these in the optional assignment. We're moving on. We're going to talk about the properties of a sampling distribution. So here they are. There's 4 properties. I typically only really focus on the ones with dashes on them, and I kind of just assume that middle one as long as the 10% condition is satisfied. I usually just assume that's true. There are scenarios where I'm worried about it, but typically I only focus on the top 2 and the bottom one. So for the top 2, this is what we looked at yesterday with the Reese's Pieces proportion of orange. So the proportion of orange in the candy machine is going to be equal to the mean of the sampling distribution. And remember, the sampling distribution, I believe I have it typed down here. Here's one definition down here. This is a totally different problem, but it's down here. There's another definition earlier, right there at the top of the screen. If I was to hypothetically do this process right here a bunch of times, take a sample of 1,500 first-year college students, like 1,000,000 times, and plot all of their sample proportions on a dot plot, that would create a sampling distribution. And the mean will be equal to the true proportion. Standard deviation, that's just a formula you need to memorize. It's actually typed on the formula chart. That 10% rule, that is true. It needs to be true. The bottom thing is very, very crucial. I strongly encourage you to make this stand out in your notes. It's called the large counts condition. I know it's typed right there, but please make it clear in your notes. If both are true, So by both, I mean n times p greater than 10, n times its complement is greater than 10. Then the sampling distribution is approximately normal. And you have to show it. You have to plug in the numbers and show that both check out. Even if it's obvious that they check out, you still got to plug in the numbers and prove it. Think of this page, these properties, as almost like citing your work in a research paper. You're proving why you're able to do the math that we're about to do on this problem. So it's important that you write all of this down when you have a sampling distribution problem. All right, let's look at one. So in this problem, let's make it a touch bigger. In this problem, we have students going to college, and a sample is taken of 1,500. And somehow they know, maybe with statistics from administration, looking at all the enrolled students, 35% of first-year students live within 50 miles of their home. In the sample, 570 of them claim that they live within 50 miles of the home. So let's practice real quick. The parameter would be P, the true proportion of first-year college students that live within 50 miles of home, and we know what it is 0.35. The statistic is what do we get when we take a sample, and that's p hat in this case because it's a proportion. We took a sample of 1,500 and 570 said they live within 50 miles of home. I mean, you could stop there, but I like to work with decimals, and when you divide those, I believe you get 38%. Yeah. So 38 is our statistic. There's another explanation of what this sampling distribution concept is. And right below that, it asks you to describe the sampling distribution. And realize, when we do this, that we will be talking about the center, the spread, and the shape. You know, in regards to CUS, what we learned back in August, we're just skipping unusual, but that's because there's nothing really unusual about this sampling distribution. So the center, we just looked at it, it was on the previous page. The mean is the true proportion. That's the mean of the hypothetical sampling distribution. The standard deviation, we need a calculator for this. We're going to go 35. Some people get mixed up and they wonder, should I plug in p hat or p? And if you know the true proportion, you need to plug in the true proportion. Divided by n, which was 1,500, and we end up with 0, 1, 2, 3. That's kind of convenient. So there's my center, there's my spread. Now I need to talk about the shape. Is it normal? Do these two things check out? And I think they do. We have a pretty huge sample, but you have to show it. Please show it. A lot of people just write that little inequality and they move on. They'll like do a check mark and they move on. They want to see that you actually checked it. So On that left one, we get 525. I'm out of room. I'm going to write it above it. You probably need to write it below it, but I'm out of room. So I would say 525 is greater than 10. 1,500 times 65 is 975. And by the way, these two results should add up to the sample size. So 525 and 975, they add up to 1,500. I learned this the hard way because I used to not teach that you had to write this whole phrase out. I used to just say normal, like I just write the word normal. But they ask you or deduct points if you don't write this. Sampling distribution is approximately normal. So you have to write the phrase sampling distribution is normal. Approximate, that's important, but not vital. All right, let's actually solve a question. We're just talking about this thing. There's an actual question, and that is, find the probability of obtaining a sample of 1,500 in which 38% or more claim to live within 50 miles of home. So a second ago, we wrote this down. We know this. We said it's normal. Think about what we could use to solve this probability problem. First of all, I like to write the question in probability notation. It does say or more, implying or equal. That's not crucial. You don't have to write the or equal. We said it was normal. We have a mean. We have a standard deviation. We can find a z-score. So we subtract those two, divide by the standard deviation, and we get a z-score of 2.4390. Now this next part, I'm going to write the calculator function. You don't have to write this part, but just for your notes, for the sake of knowing where the answer came from, it might be nice to write. So our lower bound is 24390. Upper is infinity or a bunch of nines. Leave the mean and standard deviation alone because we got a z-score. We converted it to a z-score. And we end up with 007. So this is a really convenient property or a trick with statistics. Typically, we could treat this as a binomial situation because there's like infinite college students, and we're only looking at 1,500 of them. So we're safe in regards to all the binomial properties. But in the old days, before calculators, that would be a nightmare because you're looking for probability of x being greater than or equal to 570 out of 1,500. That's like 930 binomial expressions, like terms. That's insane. So whoever it was, maybe it was Gauss, I can't remember, thought of the sampling distribution thing, discovered we could save ourselves a big headache and approximate it. Remember, I wrote the word approximate to the normal curve. It's not perfect, but it's very, very close. And if you're curious, look at the calculator. Try it binomial and try it normal CDF. You get two almost identical answers. So go to distributions and normal CDF. Type in 2.4390. and we get that 00774, or 0074. And then try and look at the binomial answer. It's binomial CDF, because we're looking at a greater than. We had 1,500 trials. We know the true probability is 35. Lower bound is 570. Upper bound is 1,500. And look how close those are. The third place is off, but it's even less than that. What is that, 10 thousandths? It's off by 9 10,000ths. That's pretty precise. So even though you have two different answers, AP actually would be willing to take both. I personally would suggest you do it this way. Anytime I see it talk about a random sample past tense that was taken, it's a hint that they're talking about sampling distributions. All right, I will see y'all in class. Have a good one.